Thank you all for getting back from lunch to see my talk, and thank you very much for the invitation. Today I'm going to be talking in the theme of what the earlier sessions today were about, really observing BVOC emissions, oxidation, deposition, interaction with pollutants to form SOA in the Southeast US. But I'm going to throw in a little bit from the Amazon. I want to highlight that almost everything that I'll show today is the work of Gabriel Isaacman and Pavel Mistal, who are currently showing posters on the same topics in the poster session. So if any of you want to see more, you'll be able to go there. And maybe many of you are there. So I want to thank the NSF and the EPA and the DOE for funding all this work. So the reason that we went down to the Southeast US was really driven by the fundamental understanding that biogenic emissions are high there, and then some observations showing that there was a very high aerosol optical depth in the Southeast US that was dominantly there in summer, and some papers by people like Anne-Marie here who showed that a lot of that may be controllable by controlling anthropogenic emissions. And so if you look at a map of the globe, you'll see that most of the green is in the tropics, and as Alex Guenther has pointed out many times, but particularly in this 2012 paper, 80% of the terpenes globally are emitted in the tropics. So we actually had two campaigns, one in the Southeast US, this isoprene volcano, and one in the Amazon, both looking at SOA from anthropogenic-biogenic interactions. So the overall picture that people, I think, have been showing is up here. I actually took this graphic from Yingjun Liu, but then I added some bidirectionality and arrows and things like that. And I just want to point out a couple of things here. This is what I'm going to be talking about are mostly in the arrows. And mostly today about isoprene, because isoprene is the dominant part of the story, so it's emitted. We make lots of oxidation products that people have been talking about. Paul Wenberg talked a little bit about the deposition of some of those oxidation products, and I'm going to talk a little bit more about that today. And then we see them going into aerosols, being transformed. And the other thing I'm going to show you today in a little more detail is the new tracers that we've measured that show a little bit more of the contribution of isoprene to SOA formation, and also the gas particle partitioning of some of those tracers that we observed for the first time in the Southeast US. So starting a little pedestrian with just concentrations, I want to make a few points. As Alex Guenther mentioned, there were two sites where measurements were made on the ground that were fairly nearby. The AABC site had a flux focus. The Search Centerville site had a chemistry focus. One thing that we know when we compare observations at the two sites made with PTR-TOF-MS is that isoprene is generally a little bit higher at the ABC site. I also want you to notice that it's quite variable during the day. And then it's much less variable as you go into the evening after the emissions stop. But if you look at the MVK and methacrylin at the two sites, they're very, very similar. Much more similar than the primary compound. And so what this tells us is the atmosphere is taking these emissions, which are heterogeneous at the surface, mixing around, oxidizing them, and the regional picture is more about the oxidation products. And so we've got to be a little careful when we're at the individual measurement sites like the search site to recognize that the emissions right at that site are not necessarily representative of the whole region. And you can also see that the monoterpene concentrations are very, very similar during the day. Maybe a little bit higher at the search site, but at night they're very different. And so the nighttime chemistry, particularly when we start talking about terpene oxidation, is incredibly local. And it depends a lot on what's happening with vertical dynamics right at the site. So again, we have to be a little cautious when interpreting the local measurements near the ground. So if we look at the actual fluxes for isoprene at the two sites, it's actually pretty amazing. The site at AABC had much higher isoprene fluxes than at Search. There's much more chemistry investigation going on at Search into what happens to these isoprene emissions. The monoterpene fluxes are almost identical at the two sites. And what this tells us is that the biology, the ecosystems in these two regions actually emit pretty differently. And so as we do our chemistry investigations, we have to keep that in mind. Going a little bit deeper into the VOC fluxes that we measured at the search site, and this is in Pavel Mistal's poster, which is right now, and we see some things are coming up, some things are going down, and some things are bidirectional. So the major things coming up are isoprene and monoterpenes. Those are colored by PAR, so you can see daytime and how cloudy it was a little bit. You see that some things were completely deposited, like this mass to charge ratio of 31.018, which includes formaldehyde and probably fragments of some other things, but you can see formaldehyde's clearly being deposited. Methylvinyl ketone and methacrylin, some of the oxidation products of isoprene that have most commonly been measured in the past, and actually there have been reports in the literature about both emission and deposition of these. We see them going both ways at this particular site. We try to look in a little bit more detail. One of the concerns with MVK and methacrylin has been that our instrumentation actually measures a sum of isopoo and AEPOX, MVK, and methacrylin. But luckily the Wenberg group with Tran Nguyen at the helm was measuring fluxes of isopoo and AEPOX. And you can see the isopoo and AEPOX flux is very clearly deposition, but the MVK methacrylin flux is not. We're measuring different things. So what I take from this is that our MVK methacrylin, the PTR TOF-MS, is not dominated by the isopoo and AEPOX. And in fact, you wouldn't expect it to be when NO is pretty high, which is actually what's happening in the morning here. In the morning, NO is quite high, 700 parts per trillion, and there shouldn't be very much isopoo and AEPOX, but yet we see a deposition of MVK and methacrylin happening at that time. Later, when the isopoo and AEPOX flux gets larger, we actually see an emission of MVK and methacrylin. And if you go to Pavel's poster, you can discuss more direct, whether this is really a direct emission from the plants, or could this possibly be isopoo and AEPOX reacting on leaf surfaces, becoming MVK and methacrylin and coming back out, a little bit like what's happening in a lot of our analytical instruments. Okay. Taking a look at the sum of all the fluxes that we can see with the PTR TOF-MS, there are about 99 organic ions that were identified with molecular formula that had significant fluxes. The emission is almost all hydrocarbons. This is dominated by isoprene and terpenes, and the deposition is dominated by oxidized stuff. One point that I want to make clear is that the deposition, these pie charts look the same, but this is really only 5% of this. So about 5% of the emissions that we see locally, they're compounds being redeposited. These are only the things we can measure with the PTR TOF-MS. Paul Wenberg showed you a little bit earlier. There are a lot of organic nitrates derived from isoprene that are being deposited. We don't see those with this instrument. So add another 10% for all of those. And anything else that can't get through our sampling line or seen by our PTR TOF-MS might also be depositing. So I think this is a rich area to think about in terms of the loss of all these oxidation products. So we had our tag instrument out there, a new version that had never been in the field before that has two different cells, one collecting gas plus particle, the other collecting just particle, and we were derivatizing so we could see a lot of these interesting oxidation products, and we got gas particle partitioning hourly for all those things. These chromatograms are very complicated. There's lots of peaks in there. And this is the particle only, this is the particle plus gas. So over the range of semi-volatile and intermediate volatility and mostly particle things that we can see, there's a lot of compounds. There's much more in the gas phase than in the particle phase. And we can pick out individual tracers like these isoprene tracers, and I'll spend most of my time now just talking about these guys, methyltetrals, methylglyceric acid, which we clearly know come from isoprene, but we're working on identifying lots and lots more things from this that I don't have time to talk about in my 12 minutes. Methyltetrals, you'd expect them to correlate with isoprene. They don't, not all the time. In fact, they correlate a lot better with sulfate, which was pretty interesting. And so thinking about connection between biogenic emissions and anthropogenic emissions, this is really what we're looking for. And if we look at the methyltetral correlation with overall organic aerosol, both SOAS and GoAmazon, we get about 0.25 or so. If we look at the correlation with sulfate, it's much better. So that tells us that sulfate is impacting the way at which these methyltetrals are showing up in the particles. And it could be that IEPOX in water is the answer, but then sulfate must be influencing particle water, and that's something Anne-Marie has been talking a lot about. If we try to look at just a summary of the contribution of methyl tetrals by themselves to the total organic aerosol measured by the AMS at both these sites, we see that in the Southeast US, they make a relatively smaller contribution than the Amazon, but overall, 5 to 20% of the organic aerosol mass is typically made up of just these methyl tetrals. The AMS data is commonly analyzed to look at particular factors that are contributing, and the IEPOX factor has been identified as one that is related to isoprene oxidation. When we compare our measured tracers, and this is in the Amazon now, the methyl tetrals actually correlate pretty well, and you can see the influence of sulfate in the colors, but the R squared here is about 0.57. Amazingly, the C5-alkene trials have an R squared of almost 0.9 with the PMF IEPOX factor, which I find completely amazing. Something that has gone through that much statistical processing and from two completely different instruments are correlating so well. And so most people have been talking about these methyl tetrals, but clearly the alkene trials are highly related to the IEPOX factor. If we look specifically at how much the methyl tetrals contribute to the IEPOX factor in SOAS and Gouw Amazon, here we're getting about 20% of the IEPOX factor mass is explained by the methyl tetrals. In SOAS, 35% in Gouw Amazon. What this says to me are a couple things. One is the chemistry's different in these two regions, but two, the IEPOX factor doesn't mean the same thing at every field campaign, and so these tracers can really help us tease apart what might be contributing to that IEPOX factor a little bit more deeply. Then finally, this is my last major point. These methyl tetrals that we observe are actually partitioning back and forth between the gas and particle phase. When the first papers started coming out on methyl tetrals in the atmosphere, they were talked about completely as particle phase tracers, and people have been measuring them mostly on filters that don't differentiate between gas and particle. They've got some gas phase absorption on them. With our instrument, we can actually differentiate. And when we compare the observed particle fraction to the predicted particle fraction, we see something really interesting. There's a hard line here that says we never get more in the gas phase than expected, but we almost always have more in the particle phase. This is true in the Amazon and the Southeast US. For pinic acid, which is something that Jose showed a little bit earlier, but in a slightly different way, the partitioning actually comes much closer to matching theory. And so there may be real differences between some of the partitioning of monoterpene products that seem to match theory reasonably well, although a little bit extra in particle, versus these isoprene products. And so we're really trying to understand why, but the equilibrium partitioning gives an upper bound to how much could be in the gas phase. Remember that these things are actually formed in the particle, and then to get to the gas phase, as far as we understand now, they have to evaporate. And so it could be that there's aqueous processes or chemical bonding or phase state kinetics kinds of interactions going on. We haven't isolated it yet. It's still a mystery. On Gabriel Isaacman's poster, he's got more than 100 different tracers that we measured with SVTAG and looking at the gas particle partitioning, and shows that the vast majority of all these oxidized species don't follow partitioning theory well at all. So that's an important thing for us to remember as we go forward with modeling. So major points, emissions are dominated by isoprene than monoterpenes. Deposition is dominated by the oxidized organic. What we could measure with the PTR TOF-MS was 5% of the observed emissions at midday. Methyl tetrals from isoprene oxidation account for 5 to 20% of the total organic aerosol and 20 to 35% of isoprene-derived SOA in these two studies, more in Gouw Amazon. Their partitioning and the partitioning of many other oxygenated BVOC products often favors the particle phase more than theory predicts. And with this instrument, SVTAG, we've measured lots and lots of things that we're just starting to pull out of the data sets. So hopefully more to come in the next year or two. Thank you very much for your time.
We have time for one question.
James.
Interesting seeing the correlation between the tracer and the sulfate in the aerosol. One of the things that may have something to do with is the aerosol acidity. I'm just wondering, did you compare that as well with the ammonia to get an idea of what the inorganic acidity was like?
So there are a variety of groups that have been thinking about the acidity of these particles, but basically our take-home, particularly looking at the SOAS, but also I think in Go Amazon, is the chemistry is not limited by acidity. These particles are acidic. That's our understanding. But certainly we need to be a little careful about that issue, but we really don't think acidity is limiting what's happening in terms of the methyl tetrol formation. Thank you.
Thank you, Alan.